Today we're going to go over one of the most frequently tested and one of the most difficult topics for most students on the MCAT. And that is the difference between gravitational and electric fields, forces, potentials, and potential energies. All of these topics are so difficult to work with simply because all the equations are very similar. We're going to be using masses, charges, distances over and over again. You'll see those variables in all of these equations, and that's one of the reasons why it makes it so difficult to select which equation you're going to use and how to apply it. Most students especially have a difficult time with this because the way they were taught this material in their physics class really was dependent on their ability to just simply plug and chug. Most likely your physics professor gave you a cheat sheet on the test that allowed you to write down all the equations, and most likely the questions were extremely straightforward, so you knew exactly which equation you needed to use and how to plug and chug the variables. The MCAT is much better at writing their questions. It is much more difficult to recognize what equation you're supposed to use, how you're supposed to use it. It's even difficult to find what variables are given to you in the passage and how you can plug those into your equation to solve for your answer. So what I'm going to do is I'm going to teach you how to think about these concepts in a much more conceptual way. So that way you're not just restricted to the plug and chug methods you might have learned in your physics class. What's really going to be essential about understanding everything we're about to talk about is understanding what a field is. So let's go ahead and start off with that. Over here I've drawn what we'll say is the Earth. So because it's the Earth, it could represent a gravitational field. We could easily though represent it as a nucleus. And in that case we could be talking about electric fields. So I like to think about fields as the possibility for there to be a force once an object enters that field. So I'm going to say that again because this conceptual definition is super important. A field is the possibility for there to be a force on an object when that object enters the field. Now keep in mind that for gravitational fields, that object is going to have mass. For electric fields, that object is going to have charge. Now keep in mind that there are objects that will have both mass and charge. But obviously if we're talking about an electric field, it will be influencing the charge, not the mass. So keep that in mind. That's the first big separation that you need to understand between these two ideas. So back to this. So again, a field is the possibility for there to be a force once an object enters that field. Now, one way I like to think about this is if you've ever seen Star Wars, you're familiar with the force fields that cover all the ships or the droids and everything. So keep in mind those force fields are really invisible, right? They're not doing anything. They just represent the possibility to stop a bullet. But you see that when that laser or bullet, whatever, hits the field, then the bullet is stopped, right? Then that bullet experiences a force. Gravitational fields, electric fields essentially work the same way. This is really just a possibility until something enters that field. But now keep in mind that there are actually two different types of fields. We have point fields and constant fields. What is the difference between these two types of fields? Honestly, it's pretty simple. A constant field is exactly what it sounds like. It is constant at every point in space. So that means that if you go farther out in space, the value or the strength of that field is still going to be the same as it was when you were closer to the center of the object creating the field. So in this case, since it is constant, there are no variables that will be able to change it, so there's no point in writing a complicated equation full of variables. So what we're just going to do is represent it with a letter. In the case of gravitational fields, we're going to choose G for gravity. In the case of electric fields, we're going to choose E for electricity. And that's it. And now for point fields, they are a little bit complicated. Point fields do acknowledge the fact that as we change our distance from the center of the object creating our field, that the value of our field is going to change. So in this case, the equation looks a little bit more complicated. We're going to use a constant G for gravitational fields times the mass, since gravitational fields are influenced by mass, and then we're going to acknowledge the fact that distance changes the value by r squared. So this is our equation for a gravitational point field. And our equation for an electric point field is actually very similar. We're going to use a different constant, k, and we're going to use a charge instead of a mass. But other than that, the equation is the exact same. And you're going to find that that is the case with all of the following equations we're going to talk about. Same idea, same concepts apply to every single one of the following equations. The only difference is that gravitational fields, again, are dealing with mass, electric fields are dealing with charge. Because of that, we're going to use a different constant in each case, but the ideas are the same. Now, as a reminder, fields are the foundation to everything else we're going to talk about today. If you really understand fields and memorize this one equation, you will be able to derive 16 plus equations that we are about to discuss. Okay, the next concept that we're going to talk about, as you can see, is a force. Now remember earlier when we were talking about fields, we said that a field was the possibility for there to be a force once another object entered that field. So in the case of our gravitational field over here, once another object with mass enters this field, it will experience a force due to the value of our field at that point. Likewise, if we were talking about an electric field, and this was the nucleus, and this was an electron, once an electron enters our electric field created by our nucleus, this electron will then experience a force. So, because a force occurs when another object enters our field, what we are going to do is we're going to add that other object, whether it be a mass or a charge, to this equation. So, essentially a force is a field times our object, and it could be a mass or a charge. So that's the essential basic idea that we need to understand for a force. So go ahead and take a second and derive the four equations for force, for gravitational point force, gravitational constant force, electric point force, and electric constant force. So now let's go ahead and walk through them together. If you're already comfortable with your answers, then you can just go ahead and skip to the end and make sure that your answers correspond with the equations that I am about to write up. So we're going to go ahead and start off by writing our field. So our field again is gm1 over r squared. And in this case, since we're dealing with gravitational fields, our force is going to be a field times a mass. So all we have to do is add our mass in. In this case, make sure that you're using m2. A lot of my students are tempted to put gm1 squared over r squared. But keep in mind that that would only be true if our two masses had equal values. And that is very rarely true. So make sure you're very careful about that. I prefer to just write m1, m2, and that way you can select whatever your two masses are. And if they happen to be equal, then great. But now for our gravitational constant field, it's much simpler. The value for our field is g. We're going to multiply it by mass, so we get mg. And that should be a very familiar equation to you. And on to electric fields. So for our point field, again, we're going to start off by just writing what the equation is for our field. kq1 over r squared. And again, remember that electric force occurs when an object enters this field. So in this case, our object could have mass, it could also have charge, but since we're talking about an electric force, we're going to take into consideration only the charge of our object, because it's the charge that will be influenced by our electric field. So our equation for electric force is going to be field times a charge. So in this case, there's our field, multiplied by q2, and there we go, kq1 q2 over r squared. Now for a constant field, again, very similar, but in this case we take our value of our field, multiply it by our charge, so we get EQ. And there you go. Now the next subject we're going to talk about is potential. Another word for potential is voltage. Voltage is something you've probably more commonly heard about in terms of electric fields, but keep in mind that it can also apply to gravitational fields. So potential and voltage, I'm just going to write it as potential here for lack of space, but just keep in mind that both terms apply. So if you're taking notes, you can write down voltage on your paper in this box as well. So potential is essentially another way to measure a field. Because again, we're not going to include our other mass or charge yet. It's simply going to be a field times a distance. So, as you can see, that would be essentially like going out into space here and selecting that distance away from the center of our object creating the field and saying, okay, what is the value of our potential here? It's essentially the same thing we did for our field. Now, whereas our field was the possibility for there to be a force once something entered that field, potential is like the possibility for there to be a potential energy once an object enters that field. And potential energy is going to be the last topic we're going to talk about in a second, and you'll see how it applies there in just a bit. But keep in mind for now, the potential is really just a different way to measure a field, and it has a different name because of that. So again, take a moment and derive the following four equations for potential. Okay, here we go. So again, if you feel pretty confident about your equations, go ahead and skip to the end of this segment and compare to make sure that your answers match mine. So now we're going to start off by writing our equation for a field, gm1 over r squared. In this case, we're going to multiply it by a distance. Keep in mind, though, that we already have a variable chosen for our distance. So we're going to multiply it by r. When we do that, this r is going to cancel out with one of these two r's. And so we're going to be left with gm1 over r. And there you go. So that's our equation for a gravitational point potential. And now on to a constant gravitational potential. So again, be very careful to use your value for a field. A lot of my students put mg here. Remember that that is a force, not your field. This is the value that you want to use. So again, it's going to be the value of our field times the distance. In this case, I'm going to choose h to represent our distance, simply because that's the way that it will most likely appear on the MCAT. Keep in mind that it really doesn't matter. We could use x, d, r, h. Doesn't matter. They all mean the same thing. They're just random variables that are representing our distance. Now on to electric fields, same idea. So we're going to write kq1 over r squared, multiply by our distance, r. Again, the values of r will cancel out, and we'll be left with kq1 over r. And then finally, for an electric constant field, we're going to have the value of our field times the distance. In this case, I'm going to use d to represent it, because again, that's the way you'll most likely see it on the MCAT. So now that brings us on to the final topic, which is potential energy. Potential energy is kind of a combination of everything we've talked about so far. In this case, it's going to be a field times the distance. So there's where we get our relationship to potential. But remember that our potential was the possibility for there to be potential energy once something entered that field, right? So what we're going to do is add that something in. In this case, the something could be a mass for gravitational fields or a charge for electric fields. So again, it's going to be field times the distance times a mass or a charge. And that's the concept that you want to understand for potential energy. So now go ahead and take a second and derive these four equations for potential energy. Okay, so once again, let's start off with our equation for a field, which is gm1 over r squared. Multiply it by our other mass, which is m2. Multiply it by an r, which will get rid of this r squared down here. So we're going to be left with gm1 m2 over r. And there you go. And then for gravitational constant fields, it's going to be, again, we start off with the field, multiply it by a distance, h, and then multiply it by our mass. And that should also be a very familiar equation to you. For point electric fields, we're going to get kq1 over r squared, multiply it by our other charge, and multiply it by another value of distance, which is going to leave us with kq1, q2 over r. And then finally, our last equation for an electric constant field is going to be the value of our field again, times our distance, times our charge. And you'll get QED. Now there's one thing I need to come back to that is going to change, and that is these two equations right here, our values for potential and values for potential energy. In reality, these two equations should both have a negative sign in front. Now the reason why is because we have essentially the wrong relationship between distance and potential energy. If you look at this equation, for example, as distance increases, what happens to our potential energy? You should have answered that our potential energy increases, okay? Because you can see that our potential energy is directly related to distance, right? But go ahead and take a look at this equation. As our distance increases here, what happens to potential energy? You should have noticed that our potential energy decreases, and that's a problem. We can't have an inverse relationship between distance and potential energy for attractive forces, because the farther two things get apart, the more potential energy they have. Think about yourself. If you were to be on the first floor of the Empire State Building and then climb all the way to the top of the Empire State Building, at which point would you have more potential energy? Obviously, you should have had more potential energy up at the top because your distance from the center of the Earth is much greater. So what we do to fix that is kind of a cheap fix. We just put this negative sign in front. So that way that negative sign can remind us that the true relationship between distance and potential energy is opposite of what it appears to be from this equation. Because what we'll get is a smaller number from a bigger distance, but that smaller number will now represent a bigger number, okay? For example, let me just put some arbitrary numbers down here to illustrate how this works. -5 is a smaller absolute value than -10, but -5 is a more positive number than -10 and therefore a bigger number, okay? So like I said, it's a cheap fix, but it's the one we've become used to. Likewise, the same rules exist for electric fields. They can be either positive or negative. And the key here is to identify whether or not we're dealing with attractive forces or repulsive forces. Attractive forces will be negative, just like gravity. Always remind yourself that gravitational forces are attractive forces. On the other hand, we do have repulsive forces for electric fields. So keep in mind that we could get the opposite scenario here, and we could get a positive value for this case, because as distance decreases, potential energy actually increases, the reverse. So keep that in mind. One really easy way to solve for that is just make sure you're plugging in the right signs for your charges. So you do get positive charges and negative charges. If you've got positive and a negative, you'll get a negative value over here, which perfectly illustrates the fact that an attractive force will give you a negative sign for this equation. Whereas if you had two positive charges or two negative charges, you'll get a positive value for this equation, which is also representing a repulsive force. So keep that in mind. I'm just going to quickly explain why this chart is so useful, and then we'll talk a little bit about how we can apply this chart in situations on the MCAT. So the reason why this chart is so useful is because essentially by memorizing one equation, learning how this equation is similar to the corresponding electric equation, and memorizing 3 very simple concepts, you will be able to memorize all 16 of these equations. And not only that, but there are a few other equations out there that MCAT prep books teach all the time. For example, there's one common equation out there which teaches what a voltage is. And a voltage is potential energy over our charge, so potential energy divided by Q. Now you could memorize the 17th equation in addition to all these ones, or you could just again refer back to what potential energy is and how it's related to potential. Potential energy is a field times a distance times a charge, and potential is just a field times a distance. Well, then obviously you're going to take this potential energy, divide our charge to be left with a field times a distance. You can see that right here. We've essentially got QED. If we want to get to ED, then we just divide by Q. Those cancel out, and that's what it leaves us with. So again, focus on the concepts. Don't waste your time memorizing all these different equations. You'll have 17, 18 plus flashcards on all these different equations, which is really not essential. The problem is when you have that many flashcards that are all memorized independent of one another, you lose sight of the big picture. You lose sight of when you're supposed to be dealing with gravitational forces and fields, or when you're supposed to use electric fields and forces. You lose sight of when you're supposed to be dealing with a point equation or a constant equation. And again, what this is going to do is allow you to focus in on the concepts, which is really the way the MCAT wants you to think anyways. Keep in mind that the test does not like to reward rote memorization. They want to reward you for your ability to really understand the concepts involved and apply them to very complicated situations. Keep in mind that only by really mastering the concepts are you going to be able to recognize when to use them in complicated scenarios. So my suggestion would be to continue to practice this chart. Make sure that you reproduce it once a day, every day, until you've fully mastered it. Again, focus on the conceptual definitions on the left, and then work on deriving every single one of the equations from those conceptual definitions. In our next video, I'll give you some examples of how you might see these equations tested.